don't know if you caught that hint there. So here's what we do. I'm not going to worry about graphing a cotangent because it literally is a tangent graph, just flipped asymptotes. So we start with one like either secant or cosecant. Well, we basically list out everything like you would normally. Secant's the reciprocal of what? Cosine. Good. So in order for us to start this, what we're going to do is label A, B, H, and K just like we would normally. In this problem, where is the B located though? So what should we do? Take it out right away, and then that way you get a clean equation. So we'll have 2 secant 2 parentheses x minus pi over 2 minus 3. Okay. That's a lot of times what they do is they will hide those things within the parentheses just to kind of annoy you, and hopefully it works. Good job. So A is 2, B is 2, H is pi over 2, and K is -3. Now, what we do here in order to graph the secant is that we're still going to graph it like it was. We graph the cosine and the cosine parent, the shift, and then what we do is we flip our ordered pairs around. Okay. Excuse me. So, plot this like we would normally. Our period then would be 2 pi over b. So our period for this is going to be at pi. Are we okay with that? So let's see. I know I have to move to the right, so I don't have to worry about anything to the left, so I can just do this. It's got to move down. So I'll extend it out a little. I'll put pi here, which means this is pi over 2, pi over 4, and 3 pi over 4. My A value was 2, so I'm going to mark it up 2, mark it down 2. And then I have space to add more to it later, or move down. Cosine graph. Does a cosine graph start at the A value or at 0? A! Starts at A. Okay, we've got not terrible. That gives us our ordered pairs. So we're at, what is that, 0 and 2. Pi over 4 is 0. Pi over 2, -2. 3 pi over 4, 0, and pi 2. Hopefully you guys are writing out when you do your ordered pairs like that. It just makes everything so clean to have the lists. All right. New ordered pairs are really, really easy here because you have pi over 2s and pi over 4s. Those are easier to work with the common denominators. So we'll have pi over 2, -1, 3 pi over 4, -3, pi, -5, that'd be 5 pi over 4, -3, and then 3 pi over 2, and -1. When you start to get these things that the shift here doesn't completely move outside of the original period. Everybody see that? Since the original period was at pi, the shift is only being pi over 2, which means there's still going to be stuff inside that original period part. So whenever I get this, and you might have been doing this also, maybe it'd be easier to move the furthest part out first, because you know that you're going to reuse at pi over 2. I know I'm going to reuse at pi over 2, 3 pi over 4, and pi, so then I have here and here to add on to. Then all I have to do is just make a couple extra spots. So let's see, pi over 2 was -1. 3 pi over 4, -3. -5. You okay with that? Okay. Where's your new 0 line? -3. My new 0 line here is at -3. Am I okay with that? The reason why I wanted to figure out where that's going to be located is because that's the easy spot to know now that if I put this as my 0, when you are at 0, what's the inverse of 0? It's undefined. So at these points here where it crosses through at 0 spots, these become asymptotes. Oh, what do you mean? No. It's okay where it's at, because what's happening here is that we're using a cosine graph, and by doing the reciprocals, we know that there's going to be an asymptote. Because if a graph crosses 0, the reciprocal of 0 is an asymptote. You okay with that? Yes, and that's why I'm just worried about those two. And tangent be the same thing, but okay. So I get the asymptote here. Now, excuse me. What happens then is, excuse me, it's actually a little bit easier to show you what's going on if I do a completely non-shifted one. 1. So we'll say it's 1, -1. Are we okay that that's a cosine graph? Yeah. So, what's the reciprocal of 1? It's 1, right? What's the reciprocal of 0? Undefined. What's the reciprocal of -1? -1. Reciprocal of 0? And then the reciprocal of 1? 1. I mark this is 2 pi over 2. Somewhere in between 0 and pi over 2 is 1/2. Okay with that? What's the reciprocal of a half? 2. So somewhere in here there's a half and it goes up. Somewhere in between here, it's diving. Because what's the reciprocal of a -1/2? Or excuse me, this point here would be -3/4. And so it's going further away. So what happens here is you get basically a blown up graph. Instead of diving downward, what's the opposite of diving downward? Going upward. And if you're here, if you're upward, what's the opposite of upward? You're downward. So you're in these sections, you're just flipping the graphs. Is really all you're doing. Okay? All you're doing is you're flipping the graphs between the zeros. The zeros create asymptotes, and you flip them. Same thing goes forward with the sine. Sometimes it's easy to see with the sine. If I do a sine graph, sine starts at 0, goes to 1, 0, opposite of 1, 0. You okay with that? What's the reciprocal of 0? Undefined. What's the reciprocal of 0? What's the reciprocal of 0? And now this one just flips up and flips down. Pretty much. No, because that's pre-calc. I'm giving you just a little bit of it. I gotta leave something for them to show you guys.
No, you don't.
So when you get back to what we were just doing here, what you want to do is, by the idea of figuring out where your zero lines go, by knowing where that shift went down, that's why we know that K value. The K value is your horizontal zero, if that makes sense, where everything crosses over. So that way I know that these 2 points become the inverses, which means this graph then, instead of being up here, it's going to go like this. Oops, I got to change color, sorry. Goes up and down and dives up. What do you mean outside? Right, but because if this is diving downward, what's the reciprocal of diving down? Moving up. Think of the fractions. Think of fractions as you're going through these things. Is if you go back into here, we know that if this is 2 pi, 3 pi over 4 over 2 pi over 2, 0. Somewhere in here is 1/2. It's here. The reciprocal of that, or I'm sorry, somewhere, this y value is 1/2. I don't know what generated it as 1/2, but I know that the reciprocal of 1/2 is 2. I know that as sine came back down, there was another value that was equal to 1/2. Yes, sir? Yeah. So when you think about where is sine equal to 1/2, sine is equal to 1/2 at pi over 3. Is that right? Yeah. Oh, I'm sorry, pi over 6. 30 degrees. Yeah, so this is pi over 6. This is 5 pi over 6. Where sine is equal here, and it flips it up. No. That's pre-calc. So, hey guys, the reason that this stuff works, and like they were just saying here, is if you think about sine within the first 2 quadrants. Sine is positive between the first 2 quadrants. Sine is equal to 1/2 at pi over 6, and then again at 5 pi over 6. So at pi over 6, sine is 1/2, but the cosecant would be 2. At 5 pi over 6, the cosecant would be 2. That's why it flips up. Same idea as it's moving downward, it flips further down then. Yes, sir?
Do we write measurements for
the flip parts?
Yeah.
No. Too messy. Way too messy. I would ask you to graph, it would look like this. You would graph the cosine, and then when you're done, you would put new vertical asymptotes in, because you'll have zeros, and just flip the graph. That's all you have to do. For us, that's all we have to do. Let me do a cosecant here. Yeah,
you have color pencils?
I don't. I'm sorry. Yeah, this is one of those things that's just kind of weird. That color pencil would be great, but I don't have it. Let's do a cosecant real fast. Let's do. Which ones? The flip-ups? Those are the actual graphs in the secants. That's a secant graph. Yeah. Right away, you should be able to tell me where your new zero line is going to wind up at.
That's what I said. Oh yeah.
Yeah, 3. It's your K value. The idea here is, guys, that that K value is going to take it from your 0. When you do your parent graph, your A value is 2. which means it's going to go up 2 down to -2, but it still zeroes out at 0 and y equals 0. When I shift that, it's going to shift up to 3. So that means my ordered pairs, wherever ordered pair lines up on 3, gets asymptotes when we graph the cosecant. That's all this really means. And then it's just a matter of blowing it up. So we have an A of 2, a B, 1, H, -pi/4, and a K, 3, gives me a period of 2 pi. All right? With a period of 2 pi and an H value of a -pi/4, that means I'm just going to have to move my graph, extend it to the left a little bit, and maybe move it up some. So let's see here. 2 pi, pi/2, 3 pi/4, 0. 2. Cosecant is the reciprocal of sine. Oh, thank you. I was thinking like, oh, I have 4. 0, 2, 0, -2, 0. Okay. If I take 8 pi/4 and I subtract the pi/4, what is my new? If I have to move to the left here, it'd be at -7 pi/4. And then if I have to move 6 pi, it would be at -5 pi/4, -3 pi/4, -pi/4, and then pi/4, and then -pi/4. What I'm doing here is I have all of my ordered pairs. If I start them out at, let's see, 0, 0, pi/2, 2, pi, 0, 3 pi/2, -2, and 2 pi, 0. To each of those, I just have to subtract a pi/4. So we have -pi/4, 3 pi/4, 5, 3 pi/4, 3, 6 pi/4, so it'd be 5 pi/4, 1, yeah, and then 7 pi/4, 3. Now, what's nice is that since this is just a quarter off of each one of them, isn't a quarter halfway between a half? So the spacing for this one works out really nice. What's that? Oh, what's 2 pi subtract quarter pi? These just went out of order because I wrote smaller and I wrote bigger since my fractions. They're still the same amount there. Yeah, it's just my handwriting's less than desirable sometimes. So I put in my new breaks. So let's see, 3. Then if you want to put that horizontal line there to help you remember that that's the new 0, by all means, there's nothing wrong with that. And if you want to throw that there to make sure you see which ones I'll hit, that's cool. And now I know that if this is a peak here, that means that somewhere in here it had to do this. If this is a valley here, that means somewhere in here it has to do this. And I go on my merry way. Yes, sir. The cosecant part? You can just do solid, because that's technically what it is. What I'm doing here is I'm doing the shift as a solid, because that's what we're accustomed to doing, and then from that I'm just, basically all I'm doing is going from the curve to blowing it up. And you can put those both solid, that's fine. Okay. And that's kind of all you gotta do.
Yeah.
So in all honesty, the only add-on problem-wise here is that you got to figure out where your asymptotes go, and then just remember everything blows up. That's all it is. It's really all it is. It's not that crazy. Next year, they'll put some extra stuff into it by like dampening and things like that. Yeah, what happens is that you can do this. Let me show you. So we'll do stuff like that next year. I'll show you. Why can't I just get my... Apparently too many. Yeah. I didn't. No, because you just fought. Because I can see it. So let's see here. The dampened sine graph. See if I can put this in for you. It's kind of cool. Where's the E button?
Wow.
Yeah, they've got a flatliner. So that's a dampened sine graph. We'll do that next year. Because what happens here is that it follows with that. Where is it? E. E to the negative x. Negative. This should work. Because if you look at this, it follows through the curves. We'll get ones like that. Show you this one real quick. And then this one. It's just kind of funny.
It's like a ball. Where as soon as it starts,
See if I gotta change the window, make it work a little bit cleaner. This should look cleaner now. There it goes. It's almost like a Batman symbol. If you flip it around, it's Batman.
No. Hey, what?
So which means I should be able to do this. If I put a negative out in front of it, would that invert it?
Yes, it's Batman. You can probably figure it out why it doesn't do that. So yeah, the other thing I wanted to show you real quick was besides all this really neat stuff, is I know a couple of you guys were having problems with this whole translation stuff. What does that mean? So as you look at, let's look at 55.